Hello, and welcome to the lecture on Chapter 13 from OpenStax Astronomy. This chapter is about comets, asteroids, and collectively the debris of the solar system. So everything that isn't a planet can be classified as a comet or an asteroid. There are some sub-classifications and some things that maybe don't quite fit as a clear comet or a clear asteroid. They're kind of a half comet, half asteroid, but this is everything that's not a planet. In the previous lecture, in chapter 12, we talked about Pluto. Well, we could have talked about Pluto in this chapter because Pluto falls into the category of a Kuiper belt object or a trans-Neptune object, an object that's outside of the orbit of Neptune, or that at least is sometimes outside of the orbit of Neptune. So what's interesting about that is it's a dwarf planet, but essentially it's just a really big comet, Pluto, all right? Now there are really big asteroids that are also dwarf planets, just like Pluto is a dwarf planet. But although to be fair, there's just one, which is Ceres. Now, that is the dwarf planet Ceres, which is in the asteroid belt. Now, if we're talking about the asteroid belt, I want to upfront make it clear that there are going to be three parts of the solar system we're going to focus on. We're going to focus on the asteroid belt, which is where the vast majority of the asteroids of the solar system are housed, are located. Then we're also going to talk about the Kuiper belt. Okay. And finally, we're going to talk about the Oort cloud. Those three locations are where asteroids or comets are located. Comets, interestingly, are either located in the Kuiper belt or the Oort cloud. Now there's a continuum, essentially. The Kuiper belt, as it becomes thinner and thinner on the very edge of the solar system, eventually becomes the Oort cloud. We'll mention this when we get to our slide on the Oort cloud and who it's named after, but this is it. These are the three parts of the solar system. All right, well, let's move on. So we're going to talk about comets. Certainly, comets are famous because they can really dominate the night sky when there's a particularly bright one. Here, shown in March 1997, was the comet Hale-Bopp, which was very bright and visible at night as long as it was a clear night without too much cloud cover. You could see it with the naked eye. It took up a angular size that was much larger than the moon when you consider the length of its tails. The brighter tail was the one that's lower down, the less blue tail. It's this one here. Although with binoculars or on a particularly clear night, you could make out the fainter but much longer blue tail. All right, and we'll talk about the names of those two tails later on. But point being, comets are quite dramatic. They've been visible with naked eye observations for thousands of years. There's plenty of historical accounts about comets well before they were understood what exactly they were. Right, they were considered potents of important events. Right, so certainly early historians, early peoples gave them a huge amount of significance. On the other hand, early peoples knew nothing about asteroids because asteroids, even if they passed near Earth, would not be visible. You need a good telescope, preferably a space-based telescope, to get good images of an asteroid. So we didn't learn about asteroids until much later on. So that the position of asteroids, as they were known in 2006, were located primarily between the orbits of Mars and Jupiter. That band of asteroids is the asteroid belt. Now, here, the size of objects are not shown to scale. You might think, oh, well, here's Jupiter, right? Jupiter's shown as a larger circle than, say, Mars. So their relative size is to scale, but the distance between them is not to the same scale as their sizes. Furthermore, the little dots that seem to completely fill in the asteroid belt are a bit deceiving because the asteroids are not that dense relative to the vastness of space between the orbits of Mars and Jupiter. In fact, if a spacecraft or a space probe was to travel through the asteroid belt, it's very unlikely that they'd even see an asteroid. There are millions of kilometers between individual asteroids. Even though there's a vast number of them, and they take up so much space in the solar system that you just have to realize how loosely packed the asteroid belt is. The total amount of mass is tiny, even compared to the mass of a planet, let alone compared to the mass of the sun, which is 99% of the mass in the solar system. So don't misunderstand that the asteroid belt is a closely packed belt of asteroids. It's not like in the movies where they show spaceships diving between asteroids. The asteroid belt is nothing like that. No, nor are probably any asteroid belts throughout the galaxy and other solar systems. So it's a fanciful way of showing it in movies. You can notice that there are also other types of asteroids that are actually in the orbit of Jupiter. Those are the Trojans and the Greeks. Collectively, those are known as Trojan asteroids. That's the type of asteroid they are. Other planets have Trojan asteroids as well, even some within the orbit of Earth. Those are asteroids that end up in what are called Lagrange points, which are gravitational balance points, so they're able to essentially stay there. Another important thing is to acknowledge why the asteroid belt exists where it does. Well, it exists there due to gravitational pulls from Jupiter. Jupiter will pull on asteroids that are located at resonance locations to its orbital period. So as Jupiter comes around in its complete orbital period, essentially a Jupiter year, there are asteroids that are going to come around twice every time Jupiter does. That means that those asteroids are going to meet up with Jupiter on a regular basis, which means that they're going to predictably get pulled towards Jupiter, basically leaving open bands that don't show up in the scale of this image, but open bands where you're less likely to find an asteroid. That means that the matter, all of the actual mass that these asteroids make up, was never able to coalesce into a planet. Maybe it would have been a small planet, right, Mars size or smaller, but it's not further enough out in the solar system to contribute a significant amount of basically of frozen gases in the form of ices to become a gas giant. So it would have been a terrestrial planet had a planet been able to form where the asteroid belt is located. Maybe perhaps a smaller version of Mars. I was going to say a large version of a dwarf planet, but more like a smaller version of Mars. But regardless, no such planet could form, not because of a cataclysmic collision, but just because of the pull of Jupiter due to resonance of periods. Okay? So that's why the best theory that explains the existence of the asteroid belt is the gravitational pull of Jupiter. Okay? But that's where the vast majority of asteroids are located. Now, the early primordial solar system would have had lots of asteroids, but those asteroids over the first few 100 million years during a heavy bombardment, and then throughout the remaining 4 billion years since then, have mostly crashed into planets, interacted with planets gravitationally, and been flung out of the solar system, but in one way or another have not allowed to persist within the solar system. Okay? The exception being the asteroid belt. Now, the asteroids that exist throughout the solar system, but the vast majority in the asteroid belt, can be grouped into 3 categories. Okay? So we can group those into S-type, C-type, and M-type, with M-type having a more of a differential history behind them. Okay? So what we're looking at is the dotted line represents differentiated, and the red lines represent primitive. If you remember, the difference there is differentiated means that a body, such as a moon or a planet, has become hot enough at some point in its history to have the denser material sink down to the middle because the planet was in a liquid or semi-liquid state, right? Or the world, right? Well, that's the story behind metallic asteroids, because at some point they were probably the core of some primordial worlds, things that could have become planets or moons, and then were broken apart, and the denser core then became a metallic asteroid. Due to that complicated history, metallic asteroids, we can see, are less common. Because if we look at the percent of total, we can see that within a distance of 2 to 3 astronomical units, and remember that the orbit of Mars is at about 1.6 astronomical unit, and then we have the orbit of Jupiter at about 5 astronomical units over here, so J and M. Well, within that, we have the metallic type asteroids exist right in the middle of the asteroid belt, but they only form about 10% at best of the total population of asteroids. On the inner edge of the asteroid belt, we see more stony asteroids. Those are the S-types. They make up over 50%, right there, of the overall population of asteroids. But the most common type of asteroid overall are the carbonaceous, C-type asteroids. These are asteroids that do have a lot of ice in them, as well as mixed with stones, and those stones are formed out of elements that have a lot of carbon in them. This is quite an interesting type of asteroid because we might think of carbon as being the element of life because all organic compounds are carbon-based for any type of life we know, and that's only life that exists on Earth, the only world we know for sure to have life. But that definitely tells us something that there's the right ingredients for life being very common in primordial asteroids. A lot of scientists then speculate on really kind of the perhaps arc of life that exists throughout solar systems in their primordial building blocks that we see left over in these asteroids. Okay? So not so much with the stony. We wouldn't have as many, of the building blocks of life in stony asteroids, certainly not metallic asteroids, but the carbonaceous asteroids is an important story there. Now, to be fair, we do also care about stony and metallic asteroids, in particular metallic asteroids, because people speculate that the future of humanity might involve asteroid mining because there's huge amounts of available metal in the metallic asteroids. Okay? So here is a piece of an asteroid. It fell to Earth as a meteor as it entered the atmosphere. So the actual event of it partially burning up in the atmosphere would have been a meteor as you saw it in the sky. But then it crashed to the ground and became a meteorite because any rock that came from outer space is a meteorite. But this particular meteorite, once collected, was identified to be part of an asteroid. It wasn't part of a planet, wasn't part of a comet, it was part of an asteroid. And furthermore, scientists were able to, based on its chemical signature, identify it as being part of the asteroid Vesta. This means we know more about Vesta than most asteroids because we have a piece of it. We didn't have to go there and collect it and bring it back, although recent space missions have done that, have collected material from asteroids and brought them back to Earth, which is much, much less energetically demanding than taking a mission to a planet and coming back to Earth, because it's relatively easy to land on an asteroid and come back because they have such weak gravitational pull. But we didn't have to do that with this one. This one came to us. All right, so a meteorite, a rock that fell from space, identified as being part of Vesta. But you might wonder, how did scientists know for sure this was part of Vesta? Well, the way that scientists knew this was part of Vesta is the way that scientists are able to identify, in general, the different types of asteroids. We look at their light signature. We look at the wavelengths of light that come off of them because different elements produce different light or reflect different light. So we're able to identify the elements through light, right? So light is used to identify the elements that make up these asteroids. Because different elements have different signatures of electron excitation within that atom, those produce particular wavelengths of light that then are matched, like a fingerprint is matched to a person, but they're matched to the element. Okay, and it all has to do with those electron excitation levels relative to the atomic nucleus. So that's the number one tool that scientists have for identifying what asteroids are made out of, or in this case, confirming that this was part of a known asteroid. All right, here are some other known asteroids: Matilda, Gaspra, and Ida. You can see that these asteroids do not have spherical shapes. It's very common for asteroids to not have spherical shapes. Only a very few do. That's because to have a spherical shape, you need to be large enough for the gravitational pull to be stronger than the rock's pull holding it together. Essentially, you need gravity to be able to just reshape rock or reshape some carbon-based elements, or in the extreme case of a metallic asteroid, actually melt and reshape the metal. Okay? Here are two other asteroids that are actually in orbit around each other, or I should say Dactyl, the much smaller asteroid, is orbiting around Ida. We see lots of examples of this. Now, you might think that an asteroid is too small to have its own moon, but that's not the case. These asteroids do have weakly interacting gravitational fields. They do contain enough matter to pull in another asteroid that's smaller than it, and then the smaller asteroid, in this case Dactyl, begins to orbit the larger asteroid. This is so important to scientists, first as just a wonderful example of gravitational interactions throughout the solar system, but it also allows scientists to measure the mass of the total system using Kepler's third law. We're able to say that the square of the period is equal to 4 pi over gravitational constant, the total mass of the two asteroids, multiplied by the radius cubed. All right. The radius would be just the distance here, or the semi-major axis for an elliptical orbit. And the total mass would be the mass, in this case, of Ida plus Dactyl. But of course, the vast majority of that mass is the mass of the larger asteroid that's being orbited. All right, so important for scientists, because that way they can identify the density of the object, because they can clearly measure its size and thus calculate its density. That's how scientists were able to start identifying that some asteroids were way denser than others, and then speculate that they were metals, and then eventually show that they did reflect light, identifying elements such as heavy metals. Now, we can see here in terms of the size, if you're wondering how big are these asteroids, they are, quite large compared to rocks, certainly. The size here is 56 kilometers, right, for Ida, and 1.5 kilometers for Dactyl. So even Dactyl is large. It's the size of a city, right? If we saw it just, on the ground, right? So a huge rock. But, considering a rock that is 56 kilometers across is amazing, right? That's a very large rock. But that is on the larger size. Most asteroids are smaller than that, but there are many that are a few kilometers across. All right? So here we see two asteroids that are actually moons. Now, once they become moons, we wouldn't refer to them as asteroids, but we sometimes still talk about their history, their origin. So we would say that these moons of Mars are captured asteroids. They've become moons, but they started their life as asteroids. Because, to be fair, an asteroid orbits the sun. Okay? Anything that orbits a planet is a moon. So these are moons that began as asteroids. These are the only two known moons of Mars, which are Phobos and Deimos. All right? Captured asteroids. Do we see captured asteroids as moons of other planets? We certainly do. Not other terrestrial planets. Mars is unique in having captured asteroids as its moons, but its proximity to the asteroid belt may explain the gravitational interactions that led to them. But we see lots of cases of the gas giants having distant moons that are in fact captured asteroids. We talked about that in the last lecture, and we pointed out that the distant moons, distant as in being far away from the actual gas planet, in the case of Jupiter, Saturn, and so on, those distant captured asteroids that are now the moons of those gas giants generally have retrograde orbits. They're actually going in the opposite direction of everything else in the solar system. All right, here we are looking at Eros, looking down on its north pole. Eros is a rather large, famous asteroid. All right, it has let's see, so the large crater, right? So the crater is 5.3 kilometers across. That's this one right here. Gives you a scale of the size of Eros. Eros has been an asteroid that's been known for a long time, so it's historically famous, one of the early identified asteroids, and it is one of the larger ones, okay? Here we are looking at the surface of another asteroid, Itokawa, all right? This one appears to have no craters, all right? So that's because it's speculated to just consist of chunks of rock and ice, so it's not dense enough to support a crater. So if something crashes into it, it probably just spews up matter that settles back down. So an asteroid like this is more of a loose conglomerate of material that's weakly held together by gravity. So it doesn't have the density to sustain actual craters, right? You need denser, stonier, or metal-based material to have that crater behavior. All right. Here's an example of a probe that was sent to an asteroid and returned to Earth, coming back and burning up in the atmosphere and breaking up. But then we actually see the part that is going to parachute down to Earth with some pieces of an asteroid successfully on its return mission. All right, and this is the Hayabusa, which was the name of the probe that went to an asteroid and came back. Okay. So here's a couple of more asteroids. One that we already talked about, Vesta, right? Very well known in terms of its composition, because a piece of it has been identified as becoming a meteorite here on Earth. All right. It is also one of the largest asteroids out there. But what's the largest asteroid of all? Which one claims the rank of being the biggest? Well, that would be Ceres. So Ceres is shown right here, and Ceres is the only asteroid that is in fact a dwarf planet. So it has the same classification as Pluto, but unlike Pluto, it doesn't have an orbit on the very edge of the solar system beyond Neptune. Instead, it has an orbit between Mars and Jupiter, because Ceres is within the asteroid belt. All right? It has a very weak atmosphere, and it is a proper dwarf planet, spherical in shape, which is one of the classifications of a dwarf planet. Okay? Here is a large crater on the surface of Ceres, all right, about 92 kilometers across. right? Quite dramatic. There's examples of some early volcanic activity on Ceres, a lot of examples of frozen water, maybe some liquid water beneath the surface. So lots of unanswered mysteries. Certainly future missions to Ceres will tell us more about this amazing dwarf planet, which is relatively close to home, located just outside of the orbit of Mars. So, if we have all these asteroids relatively close to Earth, because of course Mars is relatively close to Earth, should we be concerned about them getting pulled in and crashing into our planet? Well, certainly we should. And there are examples of quite a bit of destruction, shown, for example, here in Tunguska, where hundreds of kilometers of forest were knocked down by the energy released from a collision of a rather large asteroid entering the atmosphere and crashing to the ground. All right, leaving a meteorite behind, but also releasing a huge amount of energy. We can see a trail near Chelyabinsk in Russia, where a large asteroid burned up in the atmosphere. You may have seen all the dashcam videos when this happened a few years ago. So certainly impacts do happen. We know most famously that there was an impact of either an asteroid or a comet that caused the extinction of the dinosaurs. So we have to be always on guard and make sure we know where these asteroids are. And indeed, scientists and government organizations have been tracking the locations of asteroids and building a huge database telling us that we know most of the asteroids. We've come to a point where we're pretty sure by just continually surveying the sky that we have surveyed the majority of asteroids. And we've seen that that number has gone up quite a bit since 2000 up to 2010, and then more recently leading up into the 2020s. We can see that we've really reached a point where we're continuing to count asteroids. Now you can see that number is still going up. It hasn't leveled off exactly, so maybe there are still some more asteroids left to count, or maybe we finally got to the point where we've counted almost all of them. We can see that the majority of asteroids are actually less than 1 kilometer in size, okay? So they're even less than 140 meters in size. This yellow category here is asteroids that are 140 meters or larger, right? 140 meters in diameter or larger. They do make up a large amount of the population. Those 1 kilometer or bigger asteroids make up a very small amount of the population, considering here that the vertical axis is the cumulative number discovered, right? We can see the cumulative number of discovered asteroids is between 10 and 15,000, okay? And probably well less than 1,000 are those larger than 1 kilometer. That means those ones we've been talking about that are 50, 150 or more kilometers, these big ones that we've been talking about, are certainly the exception. The vast majority are going to be less than that, and many are even smaller than 140 meters, right? So just maybe, 30, 40 feet across, and that would fall into this blue category. Those are the smaller asteroids. Those are the least likely to be discovered because you need a good telescope and a lot of time to survey and track such small things. But we do need to know about those types of asteroids because even an asteroid that's only, say, 80 meters across can still cause a significant amount of damage if it enters the atmosphere, okay, of Earth. Here's an example of a near-Earth asteroid, Totatis, which is 5 kilometers across, so quite on the large size, and it was spinning past Earth, right, at a distance of about 3 million kilometers in 1992. And we came up with this image, what looks like a computer image, by just coloring radio data. So basically bouncing radio waves off the surface of the spinning asteroid as it flew past Earth. And we can kind of see its rotation relative to the different features on the asteroid as it's spinning around, rotating in 3D. But point being, is we tracked this asteroid as it passed by Earth. All right, and certainly a 5 kilometer long asteroid would be incredibly devastating. This would be an extinction level event for humans, right? Perhaps we would survive, but it would have a huge effect on our civilization. Okay, so now we're going to move our discussion from asteroids to comets, talking about Comet Halley, right? So famous comet, right? Here showing a composite of 3 images to resolve the tail of a comet, because that's one of the things that first comes to mind with comets is they have tails. Asteroids don't have tails. That begs the question, what's going on with comets? How are they different? Well, let's discuss that. Right? The Halley Comet is named after this early contributor to science, Edmund Halley, who lived from 1656 to 1742. His study of the sky was able to identify the comet Halley and really started speculating about what comets are and how they have very different orbits, right? They have these very elliptical orbits. They seem to move at very high speed when they pass near Earth. So what's going on? Where are they the rest of the time? Because a comet like the Halley comet only comes around every few decades. Some comets seem to come by once, and now we know with modern science that we're not going to see them for hundreds of thousands of years. So certainly no one alive is going to see that a comet again. So how is that possible that a comet can have an orbit that brings it in close to Earth and close to the sun, where it has a visible tail, and then it leaves off somewhere else in the solar system for such a long amount of time? Well, the story involves having a highly elliptical orbit, and we'll talk more about that. But let's start by talking about the tail. We're going to talk about the tail of a comet quite a bit over the next few slides, because the tail of the comet is not a single phenomenon. Indeed, as we've seen in some of the images, the tail appears to have these different pieces, what I referred to earlier as the white and blue parts of the tail. Well, the main parts of the comet tail are the ion tail and the dust tail. Now, why do they point in different directions? Well, first let's see how they point relative to the comet's motion. Shown here, we can see that the comet is traveling in this image off to the side. Neither of the tails point exactly away from the direction, which you might imagine, because if the tails created from outgassing of the comet, and we'll talk about what would cause that, but we can imagine some plumes of gas and dust spewing off from the surface of the comet, almost like it's burning up. Well, if you compare that to an asteroid that's entering the atmosphere, well, the tail of an asteroid or a meteor is directly behind the burning core of that meteorite, right? The meteorite's on fire as it enters Earth's atmosphere, and the tail is directly behind it, okay? It's a burning plume that's trailing behind it. But that's not the case with the tail. Neither of these tails is directly behind. That's because there is forces at play that end up being stronger than the small amount of inertia that these particles have. Because it turns out that the ions are charged particles that are being created by the processes within the comet. A charged particle is just that which has an uneven number of electrons and protons, and these charged particles are interacting with the solar wind. The sun produces a large amount of solar wind, which is just the name given to primarily electrons that are spewing away from the sun and flying out at high speeds throughout the solar system. This solar wind interacts with these charged ions and pushes them directly away from the sun. So we can see the ion tail has a direction that points straight away from the sun, because there's quite a bit of force. This is the electrostatic force that's driving this phenomenon, and it's very strong compared to the weak gravitational forces that are at play here and the weak effects of inertia. All right, by the way, the nucleus of this hypothetical comet here is about 1 to 10 kilometers. So I can give you some scale to the size here, kind of on the scale of large asteroids. And a lot of comets fall into this size, by the way. Comets do tend to actually be larger than asteroids. But what about this dust tail? Well, the dust tail is also getting pushed away from the sun, but not as directly. Right, so notice the dust tail is neither directly trailing behind the comet, nor is it getting pushed strongly away from the sun. Instead, we can think of it as getting pushed weakly away by the sun, because the dust tail is composed of particles of dust that are about the size of terrestrial dust, so the type of dust that's floating around your house right now, and that is on the scale of about 1 to 10 microns. And a micron is 10 to the negative 6 meters. So these are just small little particles, not on the scale of atoms. So they're the size, they're let's say about a 10,000 times bigger than an atom. So these are they're larger than molecules too, some 1,000 times larger than a molecule. They're just dust grains. But these dust grains are still small enough that they can actually interact with the photon momentum, because light carries momentum. And that small amount of momentum that light carries could actually push things. Scientists use this to pull on proteins in the biological sciences, because they need a very small amount of force to pull proteins apart. But this very small amount of force is enough to push these small dust particles. We wouldn't notice the push of light on dust particles here on Earth, because the gravitational force is greater on the surface of Earth. But here, the gravitational force to the comet's core is weak enough that the actual photon push from the sun's light is actually slowly and gradually pushing many of these dust particles away. It's not able to push away the largest dust particles, and we'll talk about those again briefly in a moment, but it is able to push away the smaller ones. So in summary, we can think of the ion tail as being charged particles, maybe molecules or dust particles, but importantly charged, that are getting strongly pushed away by the solar wind. All right, so that takes the bombardment of electrons. The dust tail is actually getting pushed away from the sun due to photon momentum. So that's the actual light from the sun, not electrons, but the actual light produced from the sun, the same light that warms up Earth's atmosphere. Well, that light is actually pushing away the small dust particles. Okay? So those are the two tails of the sun. All right? Or the two tails created by the sun of a comet. And also, important term, the atmosphere of a comet, which is just all the dust and ionized particles that are still hanging around the core of the comet that haven't been pushed away yet. That's called the coma. And the coma, you can see, is quite large in size. It's about 100,000 kilometers across. So the coma is quite a large, weak atmosphere of the small core of the comet, and that has all the components that then make the two tails. Okay, here is an actual captured comet dust particle. We can see its size as being at about 10 microns. All right, here we can see the large coma of an asteroid and the small core taken by a flyby mission. This is actually the Comet Halley, and this was taken by the European Space Agency's space probe called Giotto. All right, here we can also see two tails. We can clearly see, again for Halley, we can see that ionized tail pointing straight away from the sun, and we can see the brighter dust tail pointing at an angle away from the motion of the comet, but also away from the sun. Okay? And here are the tails, all right? Here we're really kind of showing the tails just one thing. We've sort of zoomed out so much so we can't clearly see the two tails, but notice that the tail gets larger from here to here. Because what the tail is all about is it's about the comet basically becoming vaporized. The comet started off as a solid frozen piece of ice, both water ice and other types of ices. Although primarily water ice, comets are primarily made out of frozen H2O. Other types of ice like methane and ammonia make up a very small proportion of comets on average, right? Some comets are exceptions to that, but most comets are primarily frozen H2O. All right, that's just due to the abundance of hydrogen and oxygen throughout the solar system. But we got these comets, they're totally frozen solid, but once they enter through about basically where the asteroid belt exists, so at somewhere outside of Mars's orbit, they cross that frost line. At that point, there's enough ambient energy in throughout the solar system due to the photon energy, right? Because photons carry more than just momentum, they carry energy. And that energy from the sun makes it so that the comet starts warming up. As it warms up, it starts to spew out geysers, creating that weak atmosphere, and then that atmosphere starts to trail behind, creating the tail. So you can think of a comet with this highly elliptical orbit, as we can see here, because this is not at all a circle, right? This is a large ellipse here, this highly elliptical orbit, and we can think that as the comet enters the part of its elliptical orbit that is close to the sun, it speeds up. So that's where it's moving very fast, and that's just due to Kepler's third law. And as it speeds up, it also warms up, and that's when it gets its tail. So comets, throughout most of their life, don't have tails. They only have tails when they swoop in past the sun, right? And not all comets ever even swoop in past the sun. Right, here are some more examples showing the gas tail, that's the ionized tail or the ion tail, and the dust tail, clearly pointing in different directions, okay? And we can see the motion of the comet represented by this white line. And here notice that there is a dust trail as well as a tail. Well, the dust trail represents the largest particles of the dust, almost rock-sized pieces that are a few centimeters across. And these have enough momentum and enough inertia that they're not going to be pushed away by the photon energy of the sun, and they do get left behind. Well, those left behind pieces of the comet, those then become meteor showers, because essentially the comet leaves behind chunks of matter, chunks of ice and rock, because the comet was a dirty snowball to begin with. It did contain significant amounts of rock, not just ice, just more ice than rock, proportionally. But regardless, the pieces that get left behind, well, they're floating out in space, and then as Earth's orbit passes through these leftover trails of dust, that creates those regular yearly meteor showers. That's why, if you've ever noticed, mini meteor showers you can see them on your calendar if you look up occurrences of meteor showers, because every time Earth passes through that part of the solar system, it's passing through a debris cloud left over from a comet's path, and that creates a bunch of meteors, basically those pieces burning up in the atmosphere. And very few of them would actually make it to the surface of Earth, becoming a meteorite, because again, many of them are primarily ice. Okay? Again, two tails shown here, all right, taken for the comet Mercos, okay? All right, and here is a mission that actually went to a comet and landed on it. The Rosetta mission landed on the surface of a comet. Notice that this comet looks solid with no tail, right? Well, that's because this mission happened to meet up with the comet when it was well outside of the orbit of Mars and thus was still frozen solid. So this was before the comet began to heat up and create geysers, thus creating its atmosphere or coma, and that coma becoming the tail or the two tails. Okay, so this is a frozen solid comet. Okay, with its two kind of lobes and a rocky, icy composition, very complicated surface, right? Lots of crevices. Really kind of interesting to see what a comet looks like up close. All right, and the Rosetta mission did follow the comet throughout its trajectory as it swooped closer to the sun, and actually was able to witness the beginning of its atmospheric creation, its coma, through geysers. All right, and this really told us a lot. It told us that comets don't start to boil all over their surface. They don't begin to vaporize uniformly over their surface, but indeed the heat that starts to, that is distributed onto that comet from the sun, that heat apparently starts to build up inside of the comet, creating these sporadic geysers. So it's actually a much more a unpredictable process, and one that starts in the core of the comet rather than this. You can think of the comet as just melting, right? It's doing more than that. It's actually kind of heating up and spewing out gas from inside. Okay, now what's interesting, and I mentioned this at the very beginning of the lecture, there are some objects in the solar system that can't be clearly classified as either comets or asteroids. And of course, this compounds the already complicated classification between asteroids and dwarf planets or comets and dwarf planets. Now, this is a different story. This is just straight up saying, is this a comet or is it an asteroid? And a good example of that is the object known as Chirin. All right, because Chirin has an orbit that doesn't put it in the asteroid belt at all. Indeed, we can see its orbit goes outside of Uranus and then swoops in well within the orbit of Jupiter. All right, so the orbit of Jupiter shown here in the, let's see, that would be the red one, because Saturn, no, the blue, the red one is Saturn, the blue one is Jupiter. So it swoops in well within the orbit of Saturn and close to the orbit of Jupiter shown here. Okay, and the name Chiron, it means that it's sort of a shape changer. It exists in a state of not clearly being an asteroid or a comet. And it's rare to have an orbit like this, but it's just a case in point of showing that there are lots of debris in the solar system and not all of them behave in the typical way. All right, so here is Jan Oort. Now, Jan Oort, who lived from 1900 to 1992, has the Oort cloud named after him because he was the first one that hypothesized that the Oort cloud exists. But what the heck is the Oort cloud? Well, the Oort cloud is the very edge of the solar system. It exists at some 10,000 astronomical units, and perhaps even beyond. And what the Oort cloud is it's the location of most of the comets. Also, most of these comets that exist at this unbelievable distance never come into the inner solar system. They are remnants of the primordial solar system that exist on the very edge of the gravitational pull of the sun. That's why we say it's the edge of the solar system. Because beyond about 10,000 AU, the gravitational pull of the sun is so weak that any object out there would actually just drift until it got pulled in by another star. Because at that point, we're talking about distances that approach the light year distances between stars. So the point being is that there's a spherical cloud of asteroids, of comets that exist out on this very edge of gravitational pull, moving at incredibly slow rates. And some of them get pushed just right that they essentially then fall in on an incredibly elliptical orbit that will pull them into the inner solar system. And that in some cases, they'll interact with the large planets in the outer solar system, which will change their trajectory, then changing them into a short period trajectory, where then they'll spend some number of years basically taking a shorter orbit coming in towards the sun, but that will cause them to slowly basically burn up, because every time a tail is created, some of the matter of the comet is dispersed throughout the solar system. So comets that then actually become having a period that is a few Earth years or a few hundred Earth years, well, those types of comets will only last for a few thousand Earth years, whereas comets that exist down in the Oort cloud and never come into the inner solar system, those types of comets will exist for and have for billions of years and will continue to exist, just gradually floating out there, an incredibly loosely packed cloud. So again, thinking of it as a dense cloud is completely wrong. These comets are spread out over a distance that is unbelievably vast and unbelievably cold and just on the very edge of the solar system, truly deep space. And we've never been there. right? No space probes have even come close to a distance of this great yet. Even space probes like the New Horizon, one of the space probes that's going to be, going out the furthest into the solar system, and perhaps we'll never get that far out, within a few human generations, but maybe we'll someday be able to confirm that the Oort cloud exists. But certainly it does explain where some of the very long period comets come from. Now, there's a closer in actual belt of comets, and that's known as the Kuiper belt. Now, the Kuiper belt includes Pluto, as well as Makemake and other famous dwarf planets. And this example of a temporarily named Ultima Thule. It's named Ultima Thule because Thule is the name for basically a colony that's so far away from anything else, and that's the idea here. This is one of the most distant confirmed objects so far. And this two-lobe comet, essentially, is way out there in the distant solar system and has been confirmed to exist, unlike the Oort cloud. But the Kuiper belt is just on the scale of a few hundred astronomical units. So the Kuiper belt, which right here, you can think of that as basically about 100 to 500 astronomical units. So still very far, and you can even put that 50 at the inner edge of the Kuiper belt. And what also distinguishes the Kuiper belt from the Oort cloud is the Kuiper belt is in the ecliptic plane, whereas the Oort cloud is a spherical structure. The Kuiper belt is actual a belt, right? It doesn't just have comets distributed in all the axes. Furthermore, the Kuiper belt is currently being studied. The Oort cloud is not. The Kuiper belt is known to exist. The Oort cloud is just hypothesized to. But there are plenty of comets in the Kuiper belt, and there are some that will stay in the Kuiper belt and some that will interact with other comets or the gas giants and get pulled into orbits on the inner solar system. Another thing that can actually happen to one of these comets as it gets pulled into the inner solar system and interacts with, say, Jupiter or Saturn, is it can actually then pick up speed and take a parabolic path that should just get flung out of the solar system. So instead of ending up with a shorter period, it can end up with an infinite period and leave the solar system permanently. All right, and that we've recently seen examples of asteroids and comets that came from other solar systems that actually must have experienced that same phenomenon some hundreds of millions of years ago in their solar system of origin. This is David Levy. He is a hobby astronomer, basically a amateur astronomer that has discovered many comets. Because one thing that amateur astronomers do is discover comets, because they're so hard to identify. They're so far away, right? Even obviously much further than asteroids, as we've been talking about. And these amateur astronomers can discover maybe one or two of these a year in the best case, and they can actually have them named after them. And here we have an example of a comet that was named after Levy. All right, it is the Shoemaker-Levy 9 is the name of the comet. And this particular comet is famous because it crashed into Jupiter. So this is an example of something that Jupiter does due to its large gravitational pull. It actually can protect the inner solar system from these large comets. So this comet that could have been on a collision path for Earth, very unlikely, but could have been, was instead gravitationally pulled into Jupiter and crashed. Because that's the last thing that can happen to comets when they come into the inner solar system. They can just swoop in and just go back out to the Kuiper belt or the Oort cloud, as I mentioned. They can interact with the planets and end up with a shorter period that is just every few years. They can get flung out of the solar system permanently, or they can just crash. They can just burn up as they hit one of the gas giants or one of the terrestrial planets, because perhaps the extinction event of the dinosaurs was a comet and not an asteroid. Scientists are definitely unsure about that. But this incredibly large collision included the breaking up of the Shoemaker-Levy comet as it broke into pieces due to tidal friction, and then eventually crashed into the surface. Here we can see the remnants of one of those crashes, with this basically outer, or the inner radius of that outer, kind of dark region of the collision, where a bunch of burnt up ash was created, is actually the size of Earth. Just to give you the scale of this collision. So you can imagine that if a comet this big crashed into Earth, it would devastate Earth with that sheer amount of energy. But for Jupiter, I'm sure Jupiter handled it quite well, because Jupiter is so much larger. All right, and that concludes our lecture on debris of the solar system, asteroids, and comets. I hope this lecture has been interesting and informative. Thank you so much for watching.